Hello, today I will be demonstrating my week 4 practice and demonstrate for 2300. Name is Kyle Garcia. So within this practice and demonstrate, we are tasked with designing a 4-bit prime number detector. So it's going to go between the range of 0 to 15, and it's going to be returning a 1 for any prime numbers within that data range. So for 4A, we have to actually create a K-map first. You can see over here in 4A, I create a K-map and I group the N3, N2, and N1, N0, and I have the gray code here for the numbers. And as you can see, for prime numbers such as 2, 3, 5, 7, 13, and 11, we have a 1 in there. So all that's left to do is actually group these numbers in order to reduce and simplify the system. As you see on the right, and by the highlighting, we have different groups here, whereas the green and yellow one are kind of interchangeable, so you can eliminate one of them. So we're able to group these ones together, and we can create the function as such. In this case, I actually take out the yellow one, and I keep the green one. That way I only have 4 terms. So now we can go on to the Circuitverse simulation. As you can see here, we have 4 input gates, and over here I just have them knotted and not knotted, and I just kind of string them down to make it easier to build the circuits. I use this system just because I feel it's more straightforward. So if we look at our function again, we had not, or N2 not, N1, N0. So right here we have N2 not, N1, N0, N3 not, N2 not, N1, N3 not, N2 not, N1, and then we have N2, N1 not, and N0. And basically we translated this entire function into this circuit. So let's see if we actually do have some similar responses. So remember that for prime numbers, we're going to get an output. So at 0, we don't have an output. At 1, 1 is not a prime number, so we don't have output there either. But at 2, 2 is a prime number, we have an output. 3 as well. However, at 4, we are not going to have an output. See, 4, because 4 can be broken up into 2 times 2. But at 5, there's an output. 6, there is not. At 7, there is. At 8, there is not. 9, nope, once again. 10, Oh, I'm sorry, yeah, okay. And then 12, no. But 11, there is an output. So going back to 12, 12 once again, no, but 13, I'm sorry, 15, this is 15. 15 is not a prime number, but 13 is a prime number, as we can see here. So once again, going through, 1 is not, 2 is, 3 is, 5 is, 7 is, 11 is, 13 is, but 15 is not. So for 4A, we see that this does hold true as defined in our problem or function for 4A. Now going on to 4B, we are tasked with essentially the same 4-bit prime number detector. The only difference is now our range is from 0 to 9. So anything that isn't 0 to 9 is going to be labeled as a don't care. So if we go over to my document here, we have the same table here, And we can see that for the values from 0 to 9 that are prime numbers, we have 1s. So we have 1 1s here. And from 10 all the way to 15, we have don't cares. So we can actually utilize these don't cares to further simplify the function since we don't care for them. So they could be either 1 or 0. So right here, we're able to group the 4 over here. So 5, 7, 13, and 15. And we can also group 2, 3, 11, and 10. And we can also group 3, 7, 15, and 11, but it's not really needed since all the other numbers would already be, or all the other ones would already be covered. So we can just use this pink and yellow one. So it reduces into this circuit here, which is only going to have 6 inputs. And in the first one, there were 16 inputs. I should note that as well. So we actually reduced it from 30 to 16. And in the second one, we reduced it, the second one, we reduced it from 16 to 6. Yes, from 16 to 6. So let's go ahead and look at our diagram. So remember, N2, N0, N2 not, N1. So over here it's the same setup here, just different gates on the right. So N2, N0, so that's correct. Over here, we're supposed to have N2 not right there, and N1. And just to double check, N2, 0, N2 not, and N1. Yes, so it corresponds. So in this case, we just want to make sure that any prime numbers from 0 to 9 are 1. It doesn't matter what the other ones are, because they are don't cares. So let's see. So first off, 0, no output, it's just 0. 1, non-prime number, so it's 0. However, 2, it does output a 1, because it is a prime number. 3 as well. But we won't see that happening for 4. But we will for 5. However, not for 6, but for 7. 8 is not a prime number, but it is within our range, but it's still going to be 0. Same for 9. Now, once we start getting to higher numbers, for instance, 10, we're going to see that 10 is now a 1. But that's okay, because remember, we grouped 10, and it's a don't care, so now it's 1. The same goes for 11. Even though 11 is a prime number, we did say it's a don't care, and it's grouped with a 1. And it's also 1. We can also see again over here that 12 is 0. So if we go one more number up, 12 should be 0. And we can see that 12 is 0. Right here we have 8 plus 4, 12, 0. But 13 should be 1. So if you add a 1 there, it should be 1. So yes, we find that it's true and it meets our conditions, and we simply don't care for the don't cares. And that concludes my presentation. Thank you.